Hello my dear students, in this lecture we are going to see Gauss law for electrostatics. Now my dear students, for looking at the Gauss law for electrostatics, we need some basic understanding of electric flux. So in electrostatic topic, you might have heard or you might have learned about the electric flux. So I hope that you know all the basic things and formulas regarding electric flux. Now, if you don't know, whatever may be the required part, I will explain here. Don't worry about that. See, generally electric flux is represented by phi. It is represented by phi. Now, let us understand, we have very small area. Let us say this is a very small area. I am considering very small area, right? Let us say very small area. Now, my dear students, it is infinitely small. That's why the area can be written as ds or dA. In previous lectures, we have written this area for small area as ds. But here onward, I will write dA. No problem. Exact, absolutely fine. You write ds or you write dA. It is absolutely fine, right? And my dear students, as this area vector is perpendicular to the surface, already we have seen, and the area vector is perpendicular to the surface. Therefore, let us say for the surface, if I draw perpendicular like this will be the direction of area vector, and magnitude is dA, right? And here the angle between surface and area vector will be 90 degree. This is very important, right? Already we have explained this in previous lectures. And my dear students, let us say through this surface the electric field is passing. Let us say E field is passing at some inclination angle theta with the direction of area vector. Let us say this is the electric field E field. You can say E field, right? And my dear students, here theta is nothing but angle between area vector. See, I am not saying theta is angle between surface. No, theta is angle between direction of area vector. And the direction of area vector is perpendicular to the surface. This is very important, right? Therefore, theta is angle between area vector and electric field. And then, my dear students, the flux through this area, the flux through this very small area will be very small. That is d phi. Small flux, right? Small flux through the very small area. And this is a electric field. E is a electric field, right? And this is the direction of area vector. dA is direction of area vector, and magnitude is dA. And my dear students, theta is angle between electric field and area vector, right? Theta is, we can say, angle between electric field and area vector dA, right? This is very important. And my dear students, through this very small surface dA, there is very small flux d phi, and this flux is given by, through very small surface area, this d phi is given by this electric field dot product area vector, E dot dA. This is given like this, and dot product is written as, we know that the dot product is written as, therefore d phi is equal to E dA cos of angle between them, right? This is how the dot product is written. And my dear students, how to calculate this magnitude of electric field, or this magnitude of electric field is calculated? We know that again, this electric field is calculated as 1 upon 4 pi epsilon naught, right, into Q divided by R square. This is a formula to find the magnitude of this electric field, where here meaning of each and every notation we have to understand, right? Meaning of each and every notation from the electrostatics topic we have to understand. Now my dear students, here this epsilon naught is nothing but permissivity. It is a permissivity of free surface or free space. We can say permissivity of the free space, and generally its value is 8.85. Remember the value. If you don't remember, there is no problem, don't worry about that. 8.85 into 10 to the power minus 12, and unit is coulomb square per Newton meter square. This is the unit, right? See my dear students, here I am not teaching you this derivation also I am not considering here or taking here, because this is the basics from electric flux or electrostatics I am using directly to understand Gauss law of electrostatics, right? Now my dear students, here this is a permissivity of free space which is given as value, and here Q is nothing but charge. Q is nothing but charge, and charge is always measured in coulomb, right? Q is measured in coulomb, right? And R is nothing but, see here, let us say there is a charge Q. Here I will explain. Let us say there is a charge Q placed at this point, and from this point in all direction there will be an electric field. This charge will emit electric field in all direction. And if I want to find the magnitude of electric field at some distance r from this charge, let us say this distance is r, then if I want to find E at this point, right, means let us say I will say E at this point, and then this r is nothing but, therefore r is nothing but distance from the charge. We can say distance from charge, at what distance we are going from the charge, right, in meter, dimension in meter, distance is in meter, right. So my dear students, from this you can find the unit of this electric field. Definitely you can find, put here units. Therefore if I put the units, this electric field will be equal to 1 upon 4 pi epsilon naught permissivity Q divided by R square. Let's put the units. Therefore here Q in coulomb, charge in coulomb, divided by, now permissivity in coulomb square divided by Newton per meter square into R in meter square. This meter square will get cancelled, one coulomb will get cancelled, it will become Newton per coulomb, right. This electric field is nothing but Newton per coulomb. Now my dear students, let us understand the statement of Gauss law of electrostatics. See, as per Gauss law of electrostatics, the net electric flux, here they are discussing about the net electric flux means phi. Electric flux is represented by phi. Therefore the net electric flux phi, right, it is a phi net. The net electric flux through a closed surface, this is very very important, through a closed surface, means Gauss law of electrostatics is applicable only and only for the closed surface. It is not applicable for the open surface. Closed surface means three-dimensional surface. Then the net electric flux through a closed surface is 1 upon permissivity times the net charge enclosed by the surface. It is equal to 1 upon permissivity times the net charge enclosed by the surface, right. And my dear students, it is only applicable for closed surface. This is very important. Don't apply this for open surface. For closed surface only it is applicable, right. Now my dear students, therefore for closed surface, the phi through closed surface can be written as net, here net charge inside the closed surface divided by permissivity, right. Now my dear students, again in just now we have seen through very small area, d phi is nothing but E dot dA, where dA is area vector and E is nothing but electric field vector, right. Therefore if I integrate both sides, I will get total charge, I will get total flux. Therefore if I integrate both sides, I will get flux through the closed surface, which is nothing but integration of d phi, which is nothing but integration of, it is a closed surface. My dear students, as it is closed surface, here we have to draw circle, ring like this, to show it is a closed surface. D dot E dot dA, right. Therefore simply we can say phi through the closed surface, which is nothing but, as per mathematics, it is integration over closed surface, it is a area integral or surface integral, E dot dA, which is nothing but Q net inside divided by epsilon naught, right. This is called Gauss law of electrostatics. Very very important. Now let us understand this Gauss law, or let us see the proof of this Gauss law. But in reality we cannot prove the law. Law is because of so many experimental results. It is a result, experimental result, and with the help of experimental result we are doing reverse engineering to prove this result, right. Let us see. I will consider one spherical closed surface. Now we know that the phi through the closed surface, the flux through the closed surface will be equal to net inside charge Q net divided by epsilon naught, which is also written as integration over closed surface, it is a surface integral electric field dot area vector dA, right. This is net flux inside, net flux inside. Now let us understand, if I consider one charge in a spherical surface like football, Let us consider one football. Let us say this is a football, right? So my dear students, draw the diagram properly. Let us say this is a football, like this, and at the center of this football the charge is kept of magnitude q. Now net charge inside is q, therefore can I say here q net, only one charge is kept, therefore it is q net charge inside, right? Now my dear students, here through this spherical surface the flux, the net electric flux will be equal to q net divided by epsilon naught. Now let us understand how to prove this or how to check this, right? Now my dear students, to check this, on this spherical surface I will consider very small area, and for spherical surface we have to consider circular area. Let us say if I consider very small area here, you can consider at any location, right? This is very small area vector, or this is a dA area. Now my dear students, for this area the area vector is perpendicular to the area, perpendicular to the surface, and always the perpendicular on spherical surface passes through the center. Therefore here the perpendicular or direction of dA I am showing you, this will be the direction of dA, right? It is perpendicular to surface. And my dear students, through this charge q in all direction the electric field is going, therefore the electric field is also going in the same direction, like this. This will be the direction of electric field. Through this charge q in all possible direction the electric field is going, therefore electric field direction is also this. Therefore can I say the angle between electric field and area vector is 0 degree. Here angle between electric field and area vector is 0 degree, definitely. Therefore let us find d phi through this very small area. Now d phi is nothing but E dot dA, just now we have seen, which can be written as this d phi is equal to E dA cos theta, and cos theta is cos 0, cos 0 is 1, therefore this d phi through very small area will be E dA cos 0, and cos 0 is 1, therefore it will become E dA, right? This is the magnitude of net flux passing through this very small area. Now my dear students, as I have considered area at this location, what is the distance? Now the area I have considered at radius r, the area I have considered at radius capital R. Now let us consider area at any other location. If I consider area at this location, you can consider at any location. Let us see this very small area dA. I can change the location of area. Again at this location the direction of area will be perpendicular to this area surface which passes through the center, therefore it will be direction of area vector dA, right? And again the electric field at this location will be in all possible direction, electric field is going outward from the charge, therefore same direction, means again theta is here 0 degree. Therefore again my dear students, at this location the d phi will be equal to E dA, right? Now let us check the value of E, whether the E is constant at each and every location or not. Now I can change the element, I can change area here also, I can take area here also, I can take area at any location, my dear students, right? At any location if you take area, the area vector and the electric field vector you will find in same direction. You can go at any location, you will find they are in same direction, means angle between them at each and every location is nothing but 0 degree. You can check any location, angle between them is 0 degree. Now let us check the magnitude of this electric field, or E is equal to, we have seen 1 upon 4 pi, it is epsilon naught, then into q divided by r square. Now here while considering area, I have considered this area always at radius r, always at radius r only I am considering this small area dA, right? So my dear students, this radius r is nothing but this distance of charge particle from the area is nothing but capital R here, therefore here r is always constant here, therefore E is equal to 1 upon 4 pi epsilon naught q divided by capital R square here in this case, which is always constant while considering element on the surface. This R square is always constant, therefore my dear students, here I will say the magnitude of electric field is constant. Yes, direction changes, yes, direction is changing, but the magnitude of electric field is constant. Therefore my dear students, to find total phi or flux, this d phi is nothing but EdA, right? Here we have proven this. Now to find total flux, we have to integrate both side. Right? So my dear students, if I integrate, then I will get this phi, total flux will be equal to E is constant into integration of dA. If I add such all small areas, then I will get total area of the sphere. If I add such very small elements, infinite elements means integration, right? Then I will get total area of sphere. Surface area, my dear students, all the elements we are considering on the surface of the sphere. Therefore, we will get surface area of the sphere. And my dear students, what is the surface area of the sphere? It is 4 pi r square or not? It is 4 pi r square. You must know the surface area. Therefore, it will become E into A. Therefore, let us put the values. E is nothing but 1 upon 4 pi epsilon naught into Q divided by R square. This is the E value into area is 4 pi R square. Surface area is 4 pi R square. Right. Now here you can check. 4 pi R square will get cancelled. Now only remaining is Q divided by epsilon naught. Therefore, my dear students, here this net flux phi, which is nothing but integration of E dot dA, is again equal to, for a closed surface, this is very important, this is only for the closed surface, is equal to net inside charge divided by epsilon naught. And the same is called Gauss law of electrostatics. The same is nothing but Gauss law of electrostatics. Now you have to remember this law always. Now from this law, can you say the net flux from a closed surface is nothing but it depends on only the net charge and permissivity. It depends on permissivity and net charge only. It do not depend on the radius as well as the shape of the object, closed surface. Now let us understand. So my dear students, net flux through the closed surface is the electric flux. It is the electric flux, remember, right? The net electric flux through the closed surface is nothing but closed integral. It is a closed integral. For a closed surface, it is a cyclic integral or closed integral of electric field dot area vector dA, which is also given as Q net inside charge divided by epsilon naught. Right. Now here can I say this net charge, which is here, it is a phi for a closed surface. Surface must be closed surface, very important. Closed surface is also called Gaussian surface. My dear students, closed surface is also called Gaussian surface. Don't worry about the closed surface. I will show you what are the different types of closed surface. It is also called Gaussian surface. Right. So my dear students, for this Gaussian surface, we can also say 3D surface, 3-dimensional. It is not 2D. Don't consider circle. If you consider circle, you are wrong. Circle is not closed surface. It is an open surface. Only sphere, cylinder, cube, these are the closed surfaces. Right. And here this Q net is a net inside charge. It is not outside charge. We have to consider the net inside charge only. And this we have seen permissivity. Right. This we have seen permissivity. Now, my dear students, therefore, the net flux depends only on the net inside charge and permissivity, and it do not depend on the size and shape. Therefore, we can say shape and size of a closed surface do not affect net flux. Do not affect net flux. Very important, very important. Understand this, right? Means, let us say here, if I consider Q charge and let us say closed surface of radius r, right? Let us say closed surface of radius r or closed surface of radius 2r, or if I consider closed surface of radius 2r, or if I consider closed surface of radius 3r, let us say this is a closed surface of radius 3r. Now through all these surfaces, the net flux will be same. Means, see, from this Q, the flux is going in this direction, in all possible direction, the flux is going like this. Electric flux is going like this, right? In all possible direction, right? Means, my dear students, whatever the flux coming from the first circle is, or first sphere, small sphere, it is not circle, right? From the first sphere is same, from the second sphere is also equal to from the third sphere. The same flux is coming out, right? Therefore, again, my dear students, In the other language, we can say through charge q, we can say through charge q by epsilon naught flux comes out. Flux comes out. Likewise, also I can say, right? Q by epsilon naught flux comes out through charge q. Now, at any radius, what is the here flux? Phi will be q by epsilon naught. Radius is independent of radius. Again, it is independent of shape also, my dear students. Let us say I have cube. Let us say I have cube like this, right? I will consider cube like this. And my dear students, the charge is kept at the center of cube. It is at center of cube. Don't consider it on the surface. It is at center of the cube. Now through this cube, in all possible direction, the flux will come. Through this cube, in all possible direction, the flux will come outside, right? Let us say if I have cylindrical surface, I may be having cylindrical surface also like this, right? Let us say this is a cylindrical surface and charge q is kept at the center of cylinder. Now through this cylindrical surface also, in all possible direction, the flux will come out. It will come out in all possible direction, right? Again, you can be having here conical surface also. You can be having conical surface also. But the condition, my dear students, is the charge is kept inside. The condition is the charge is kept inside. It is not on the surface. Charge should not be on surface. Let us say you have one conical surface like this. And charge is inside, my dear students. It is not outside. So from this conical surface, the charge coming in all direction. For all these cases, the flux is nothing but net inside charge divided by epsilon naught. For all cases. And the condition is charge is always inside. Now let us understand few cases. Now let us say the first case I am assuming that the first case, let us say this is a closed surface, any surface, right? This is a closed surface, but the charge is kept outside. Let us say the charge is kept outside. Now in this case, what will happen? Now because of this charge, see the electric field emitted from this charge is also passing through this closed surface. See, the electric field emitted from this charge is also passing through this closed surface and also passing through other points like this, right? Means this closed surface is coming in contact with this electric field also, right? Now in this case, what happens? Let us understand. Now my dear students, what I will do, on this side I will divide this field, this surface, like in two portions. I will divide this surface in two portions. Now let us consider the right side of the portion. Now if I consider here area, very small area, right? Through this small area, the area vector will be like this. See, area vector will be like this, dA. And electric field is also on the same direction. Electric field is also on the same direction, right? So my dear students, here can I say, here on this, let us say this is element number 1. On this element number 1, what will be d phi 1? D phi 1 will be E dot dA, which can be written as E dA cos theta. And here both are going in same direction. Means cos theta is cos 0. Cos 0 is 1. Therefore, it will become E dA. Or E1, we have to write, truly speaking, we have to write E1. E1 dA. We can say d phi 1 is positive. Right. Means any area considered on the right side of this section will be having positive flux. Let us understand. If I consider any other area, let us say at this location, right, at this location, let us say this is the area vector dA and it is the electric flux vector, right? Again, both are in same direction, means positive. If I consider area here, somewhere here, let us say like this. Now again at this location, this will be the area vector dA. This is the electric flux. Angle between them theta is definitely theta is less than 90 degree. Means cos theta will be always positive. First quadrant, na? It is the first quadrant. Cos theta is always positive. Means d phi is always positive on right side. Here I can say on the right side of the section. Right side of the section. Now let us consider left side of the section. Now my dear students, if I consider area element here, let us say this is the second element. Second element. Now for this element, the flux is or electric field is towards right, But my dear students, for closed surface, the area vector is perpendicular to surface in outward direction. Already in previous lectures, I have discussed this with you, right? For a closed surface, the area vector is always perpendicular to the surface and outside the surface. It is going away from the surface. Therefore, at this location, area vector will be like this, dA. Right. Now, at this location, you can see the angle between electric field and the area vector is 180 degree for this shown location. Or in this on left side, the theta is, here we can say, more than or equal to 90 degree, we can say. Means in second quadrant cos is negative. In second quadrant cos is negative. Therefore cos theta is negative here. Right. At this location 180 degree. Therefore d phi 2 at 2 location it is E2 dA cos theta. Cos theta is 180. Cos theta is 180. Right. Yes, electric field will be different as location to location. As the distance of the area changes, electric field magnitude changes. Don't worry. But what I am trying to tell you, on the right side all fluxes are positive, on left side all the fluxes are negative, and the positive and negative fluxes are same. The magnitude of positive fluxes is equal to negative fluxes, and addition, the net will be 0. That's what I am trying to tell you here, which will become minus E2 dA here, right? Means, my dear students, any section, let us say area is considered here. This is the area vector dA, right? And here electric field is passing in this direction. This angle is more than 90 degree, right? Means second quadrant. In second quadrant, the fluxes are, or in second quadrant cos theta is negative, therefore the flux is negative. Therefore, for this area or any shape, you can consider any shape. Let us understand the shape is like this, right? And charge is kept here. Now here the half fluxes will be in this direction, half fluxes will be in this direction, and half will be in this direction, and this half will cancel this half, and the net flux, what I am saying, the net flux, which is nothing but q inside net divided by epsilon naught, and inside there is no charge, which is equal to 0. There is no inside charge. This q is outside charge, this q is outside charge, therefore phi net will be 0 in this case. This is very important step, my dear students. Again, let us consider second case, case number 2. Now inside charge I am considering, see, in wording, no need to tell this case. Let us say inside charge there is a q1 inside, q2 inside, and q3 outside, then my dear students, what will be the net flux here? In this case, the net flux will be, the flux is because of the inside charges, therefore it is q1 plus q2 divided by epsilon naught, which is nothing but here cyclic integral over the closed surface E dot dA. And now, my dear students, very interesting point I will tell you here. q1 plus q2 is a net inside charge, right? Therefore q net inside of the closed surface we have to consider q1 plus q2. To find net flux, we have to consider net inside charge, but this electric field is a net electric field because of q1, q2 and q3 also. Here, while using this formula, this E is nothing but net electric field, very interesting, but this E is nothing but net electric field. It is a net electric field due to all charges, all inside as well as outside charges. This is very interesting, but the thing is that because of outside charge, the net inside field will be 0, net inside flux will be 0, but there is an electric field, my dear students. Because of outside charge, there is an inside electric field, but the flux is 0. Already we have seen just now, right? Because of outside charge, there is an electric field, but there is net flux is equal to 0. That's why this electric field is considered for q1, q2, q3 all together. This is very important, right? Again, my dear students, let us say the third case is case number 3. Let us say inside a closed surface dipole is kept. Inside a closed surface, I can say inside a closed surface, electric dipole is kept. Then what will be the net flux? Tell me answer. Tell me. Pause the video and tell the answer. What will be the net flux? See, what is electric dipole? Now, my dear students, electric dipole is nothing but one positive charge and one negative charge. It is like couple. In mechanics, you understand the couple. What is the couple? Two equal and opposite forces. Two equal and opposite forces cause a couple. Similarly, two equal and opposite electric charges form a electric dipole. Let's say this is a closed surface. Here there is a plus q charge and a minus q charge. Plus q charge and minus q charge of same magnitude are separated by very small distance e. Are separated by very small distance e. Right. See, two equal and opposite forces are separated by some distance is called couple. Two equal and opposite charges are separated by some distance is called electric dipole, which is responsible for rotation. The rotation of fan. If you switch on the button, the fan starts rotating. Means at fan there is an electric dipole which is responsible for the rotation of fan or electric charge. Right? We can say electric charge. Right. Now, my dear students, therefore, because of this dipole, what is q net? Now, net inside charge is plus q minus q, which is 0. Therefore, net flux will be equal to here net inside charge 0 divided by epsilon naught, which is equal to 0. Therefore, because of electric dipole, the net flux will be always equal to 0. Now, my dear students, let us understand some interesting facts regarding Gauss law. Now, my dear students, this Gauss law is always applicable. This Gauss law is always applicable, but always it is not useful. But always it is not useful. Very, very important. Now see, we can apply always the Gauss law, but in some cases it becomes very critical and the calculation becomes so lengthier and so difficult that no one can solve these calculations. So under such condition, this Gauss law is not useful, right? But yes, we can apply. But the calculation becomes so difficult that no one can solve these calculations, right? So my dear students, in book sometimes it is written as the conditions to apply Gauss law. So here also we will see the conditions to apply Gauss law. See, Gauss law can be applicable anywhere, but we are not applying always because the calculation part is very much difficult afterwards, right? Therefore, in which condition we are applying Gauss law so that the calculation becomes simple, that we are understanding, right? Conditions to apply Gauss law, right? Number one is very first condition is the Gaussian surface. Gaussian surface means it is a closed surface. Already we have seen, right? The Gaussian surface, which is also closed surface, right? The Gaussian surface should be symmetric about the charge. Should be symmetric about the charge. About charge q, right? This is important. Charge is nothing but q, right? This is the first statement, right? If Gaussian surface is symmetric about the charge field or charge distribution or charge, then Gauss law application becomes simple. Yes, if it is not symmetric, we can apply, but the calculation becomes difficult. Second is electric field must be symmetric or equal or constant or same. Here electric field must be symmetric, or we can say must be equal or same, or we can say constant, right? At all points of the Gaussian surface. At all points of Gaussian surface. Gaussian surface means where we can apply Gauss law or closed surface, or it is a closed surface, right? Again, electric field must be symmetric, then only calculation becomes simple. Then third point to apply Gaussian law is theta angle between electric field and area vector. The theta, that is angle between electric field and area vector, must be same at all point of the surface. Must be same at all points of surface. For our case, theta is generally sometimes 0 or sometimes 90 degree, but it can be 30 degree also, it can be 60 degree also, it can be any value, right? But if theta is same at each and every surface, then this Gauss law is applicable, right? It is applicable. Yes, for other condition also it is applicable, but not useful because the calculation part becomes so much lengthy, right? So these are the conditions where we have to apply Gauss law. And the last condition where we are applying Gauss law is the Gaussian surface must not pass through the any charge particle, right? Gaussian surface Gaussian surface must not pass through any charge particle or point charge, or we can say point charge, right? Means the point charge should not be on the surface. The point charge should not be on the Gaussian surface, then only it is applicable or useful, right? So my dear students, what we will do in next lecture, we will see some numericals on this Gauss law of electrostatics.